Okay, let's wait for 2 more minutes. Then we will start. Okay, I think my PPT is visible.
Yes, sir.
Yeah, okay. If you face any error in my audio and in my PPT, please let me know. Okay. So good evening, everyone. My name is Amit Kumar Sharma, and today we are covering week 2, live session number 2 for energy conservation and waste heat recovery, a NPTEL course from course instructor Professor Prashant Kumar Das and Professor A. Bhattacharya from IIT Kharagpur. So every Friday from 7 to 9, we are covering the previous week. Yeah, please mute yourself. Yeah, okay, thank you. So every week we are covering the past week sample questions, so that these will be helpful in your the current assignment. Dr. Krishna, please mute yourself. I think your background sound is coming. Dr. Krishna. Okay, please, if you want to speak something, then only unmute yourself. Otherwise, I request you all, please be muted. Okay. So today we are covering week 2 class. Okay. So last week we have covered the week 1 course content, and in which we have solved, I think, more than 20 problems, and we have also discussed in the class, and it was it was a very good session, and everyone participated in that session. So I request you all today also please participate in the question solving. Okay. Now I request everyone, are all in the are all were present in the previous class, or anyone new here today? Please let me know. Okay, anyone new today? Okay. Am I audible? Hello.
Sir, you are audible.
Yes, sir.
Okay, okay. So, okay, I think everyone is from everyone was also present in previous class. If anyone is new today, please I request you to introduce yourself. Okay. Okay, let's start with the questions. So the first question is the Carnot cycle consists of. So we have given the Carnot cycle and we have given the 4 options. So in 4 options we have given like option A, 2 reversible adiabatic, 1 constant volume process and 1 constant pressure process. Option B, 2 isothermal, 1 constant volume and 1 constant pressure process.
Excuse me.
Yeah.
I think have you changed the slide?
Yeah, are you not able to see the slide?
We were able to see the means I am able to see only the title slide.
Okay, let me check. Yeah, I request Gayatri, please mute yourself. Yeah, otherwise I have to mute you because some background sound is coming from yourself, from your mic. Are you now able to see the second number slide? I am on slide 2. Are you able to see? Question number 1. Anyone able to see the question number 1? The Carnot.
I'm unable to. I'm not able to see. Please request others. Can you see?
Anyone else? Please confirm. Okay, let me reshare my slides. Maybe there is some issue. Let me reshare it. Are you able to see now?
I'm able to see your only first slides. Yeah, now it's fine.
Okay.
Thank you.
So the question number. Yeah. Okay. Thank you. So the question number 1 is the Carnot cycle consists of. So we have 4 options A, B, C, and D. So take 2 minutes and go through all the options and try to recall the class notes. And based on that, please try to answer.
Sir, option D, sir.
Okay, option D. So we have one answer, option D. Anyone else?
Yeah, it's option D.
Okay. Let's wait 1 more minute and try to recall like which process is adiabatic and which process are isothermal. I will ask them also. Like what kind of process we will discuss it here. Like what kind of 4 process are there in the Carnot cycle. Try to recall everything so we can discuss it. Let me meanwhile draw the cycle. Okay, so the correct option is option D. So there are 2 reversible adiabatic process and 2 isothermal process. So let me draw the cycle. So anyone, what will be the x-axis? What should be here, pressure or volume? On x-axis?
Pressure. X-axis is volume.
Yeah, volume. On y-axis?
Pressure.
Okay. So there are, what will be the first? Suppose this one is the point first. This is point 1. So there will be a process 1 to 2. So what will be like this?
So it can be heat addition, isothermal process.
Yeah, first will be the isothermal heat addition.
Heat
Okay.
addition.
Yeah, maybe like this, and then it's 0.2. Actually, my drawing is very bad. Okay, so please just understand the concept. And the second process from 2 to 3, what will be there?
Adiabatic expansion.
Yeah, there will be adiabatic expansion. And again, it's 0.3. Now there will be 0.4. So 3 to 4 will be?
Constant temperature heat rejection.
Yeah, it will be constant temperature heat rejection. Yeah, this will be 0.4. Okay, now there will be another process 4 to 1.
Adiabatic compression.
Adiabatic compression. Okay, so there are these 4 processes. Okay, 1, 2, 3, 4. So this process number 1 and 2 are isothermal. So T will be constant. Okay, and process 2 and 2, 3 and 4, 1 are adiabatic. Okay, so the 2, 3 adiabatic compression, adiabatic expansion, and 4 to 1 is adiabatic compression. So this is a Carnot cycle. It is reversible. So either you can go from 1, 2, 3, 4, or you can also go in reverse manner. Okay, any doubt? Okay, let's go to the question number 2. So the question number 2 is, which of the following are causes of irreversibilities? So I think everyone is aware of irreversibility, and what are the main causes? So one is friction, second viscosity, then mixing, then pre-expansion, then heat transfer across a finite temperature difference. Go through all the options and try to also recall the reasoning, because we will discuss the reasoning also. Yeah, take 2-3 minutes and then we can discuss.
It's option D.
Okay, so we have one answer, option D.
Yes, sir.
Option A. Okay, now we have contradiction here. Okay, so it's going to be a very good discussion. Try to recall the reasoning also. If you are saying like option D, then you should have reasons for all the options why all the options are correct. If you are saying option A, then you should have reason that why other
Can
options
I-
are incorrect. Okay, let's start
Can
with
I just-
option A. Yeah, please. First, we will go with option A. Who was saying option A? Please explain your reasoning. I think someone was saying option A is correct. I request him to please discuss it. Okay. Okay, let's go with option D. Then who was saying option D? Please discuss it.
Sir, okay, coming to the option D, it's like if I go with the friction, so if any process, if you are moving a block from just block on any surface, due to the friction, heat will be released, but you are placing it to the same point again, heat will not regain back again. So that is one thing where irreversibility, as it is showing some effect on the surroundings. So that is the first thing.
Yeah,
Viscosity,
right,
I'm not sure about it. I'll come back. I'll come at the last about the viscosity. So mixing also same thing. When you're mixing two liquids, due to the chemical reactions, you might get heat liberated. Doesn't mean that if you separate, the heat will come back again. It's like some effect on the surroundings and the system. free expansion also the same case where it will be expanded without through the vacuum. That is one thing. Heat transfer across the finite temperature difference. I am not much sure about the reasoning for this option. It's like I have a basic idea, but I'm not much sure about it.
Okay.
And
Do you want
with the
to?
viscosity also.
Yeah. Okay. So do you also want to put some light on what is the irreversibility? What do you think of irreversibility?
So irreversibility is suppose if there is a system in a surrounding, if I bring the system from one point to the other point, if the system shows any impact on the surrounding, and if the same process if I am regaining it back, if it is if that effect was getting absent or if it is removed, such kind of processes are known as reversible processes, and the rest all the other processes are known as irreversible processes. Due to this irreversibility, what can I say that the efficiency of the heat engine or something like that will reduce because we are unable to use the complete utilization of the thermal energy will not be done due to these kind of factors. So that's what I can say.
Yeah, correct. So basically, if suppose we are two states, state 1 and you can say state number 2. Okay, so there is a process 1 to 2. If I say the process 1 to 2 is reversible, okay, so this means that if I'm going from state 1 to 2, okay, so there is some effect on the surrounding, okay, and there are some other effect also during the process. So when I again go from 2 to 1, then the same effect is reversed. Okay, suppose from 1 to 2, this process is liberating maybe 10 kilojoule of heat. Okay, so in 1 to 2, and suppose at 1 the temperature was 350 Kelvin, at 2 maybe 250. Okay, so again when I'm going from 2 to 1, so again this process will gain the heat from surrounding equal to 10 kilojoule, and again gain the temperature 350 Kelvin. Means the both end state will remain same. The end condition will remain same. So there will be no energy loss. Okay, so you are going from a point 1 to point 2 through a path. Okay, so there are 2 points, 2 states. You are choosing a path. You are going from a path. Again, you are returning from the same path, and you can see that the states are the properties are those states are same. So that will be the reversible process. But in actual, it's not possible because whenever you choose a path, okay, so on that path there will be various type of irreversibilities. So they will like you can say resistance. They will resist the energy. Okay, so there will be some losses to overcome those resistance. So in those overcoming resistance, some part of energy will get lost. Okay, so there will be the loss of energy will be there during any process in real process. So you cannot come to the same state. Okay, and the same effect cannot be reversed. The heat which is suppose if you have lost the heat to surrounding, so your process cannot take directly heat from the surrounding. Okay, it cannot take directly the same amount of heat. So the friction is one part. Viscosity we can discuss in like suppose if we are mixing gases. Okay, so the gases are also having and we are mixing like some liquids. Okay, so in that part viscosity can come to play. And mixing, you can also know the mixing is also like if we are mixing, so the temperature get the molecules are having some their kinetic energy. Okay, so and then if we are mixing some gas molecules, then they will again like if like their kinetic energy will change, and there can be reactions also like chemical reactions also. Okay, so it depend on the gas. There can be chemical reaction, If you go on molecular level, then then mixing can change their kinetic energy, their potential energy, and everything. The similar case like free expansion also, and in heat transfer also. Because if we are doing a heat transfer from a finite temperature difference, suppose a body A and body B. Okay, so it is at 1000 degrees centigrade, it is at 500 degrees centigrade. If there is a heat transfer, so some heat will be lost, heat loss in the surrounding also. So that heat loss cannot be recovered. Okay, and we cannot transfer heat from 500 degree to 1000 degrees centigrade. Okay, because if you want to transfer heat from low temperature to high temperature, then we require a device and we have to give some input energy. Okay, because that we have covered in the second law of thermodynamics. So it's also not possible. So there will be always irreversibility. So everything is cause of irreversibility. So the correct option is option D. 1, 2, 3, 4, and 5. Okay, I think it's clear. Okay. So question number 3. What is the closest principle is expressed as? We have 4 options, A, B, C, and D. Please go through the options and tell me the correct answer. And also try to think like what option A represent, what option B represent, and try to recall everything. Yeah. Take 2 minutes.
Sir, option B, sir.
Okay.
Option B.
Option B. Okay, so we have I think 3 to 4 answer for option B. So I think option B is correct. So the correct answer is option B. Now let's start the reasoning. So what about option A? If option B is correct, then what is option A representing? Anyone?
So option there, it's not a possible process if it is greater than 0 means such kind of process is not. But means these are the, it's not, it depends for the cycle. Sorry, I shouldn't say it's possible. Cycle related thing. So such kind of cycle is not possible. And if it is a cyclic integral of dq by t is equivalent to 0 means it's like it's a reversible cycle. And if it is cyclic integral of dq by t less than 0 is irreversible cycle.
Okay. Anyone else?
So it's
So the change of entropy will always be greater than 0, sir, for irreversible process.
Okay.
So for reversible process, the delta S change of entropy is equal to 0, but it will not be less than 0 for any cases. Practically, it is not possible.
Okay. So what about the option A? Is it correct or not? So correct answer is option B. What about option
B
A?
is, option A is not correct, sir.
Option A is not correct. So what is the meaning of option A? Like you are saying that entropy of the system or entropy of the what? What were you telling?
Entropy, the change in entropy of the system will not be less than 0.
Okay.
It will be always greater than 0 for actual case. For ideal case, it will be equal to 0.
Okay. So option C is representing the, as I
Option,
think one of you said the option, if del q by t, cyclic integral of del q by t is 0, it means that
it represents a reversible cycle.
Yeah,
Reversible
it is
cycle.
reversible cycle, correct, because we are talking about cyclic integral. So it will be reversible cycle. If del q by t is less than 0, mean what is this?
It's irreversible cycle, sir.
Yeah, it will be irreversible cycle, and this will be representing the closest principle. Okay, and if this is the
For a
case
cycle.
for a cycle, then the cycle is not possible.
Possible.
Yeah. So maybe
So
maybe there will be a question in your maybe assignment or maybe in your exams that you have two cycles, then you have to identify that is it cycle possible or not. So you can check from this closest equation that this cycle is possible or not.
So we can say that if any between any temperature limits, if there is any energy transfer,
Yeah.
and if it is forming a cycle, so based on this equation, we can this is the criteria which it should pass, right?
Yeah.
Is that the thing?
Yeah. Same thing. Correct. So if there is a cycle, so you are having like so you are having like some interaction between some temperatures. So with the data available with you, you can apply this equation and you can find out that if these lie within the closest principle, then that is cycle is possible, and maybe it will be irreversible or reversible. But maybe sometime it is also not possible. So you can check with delta Q by P. Maybe we can see some examples in our discussion also. Yeah. So choose the correct statement for the TS diagram shown in figure 1. So we have a figure, we are having a TS diagram. So you have to choose the correct statements. So there is a mention about option A, area 1265. 1, 2. So here will be 1, 2, and 6, 5 represents the heat added to the cycle. Area 4365. 4365 represents the heat rejected by the cycle. Area 1, 2, 3, 4 represents thermal energy converted into work output. All of the above. Go through the options, take 1 to 2 minutes and tell me the answer. And also recall like which cycle this diagram represent.
So the answer is option D, sir.
Oh, very quick. Option D. Okay, let's
And
wait
the
for 1 or
cycle
2 more
is
minutes.
Yeah, it's option D.
Yeah, okay. Option 2. Option D. Okay, so now we have 3 answers for option D. Yeah, correct. The correct answer is option B. Now please name the cycle. Which cycle is this?
Carnot cycle.
Yeah, it's Carnot. Okay, Carnot cycle. So it is a TS diagram. So the horizontal line is representing the temperature and the vertical line are representing the S entropy. Okay. So 1 to 2. So the temperature is constant. Suppose T1, 4, 3, temperature T2. So temperature T1 is constant for 1 to 2. So it will be isothermal process. Isothermal. And 3 to 4 is also isothermal. T equals to constant. Now 2 to 3 and 3 to 4, we can see the, suppose this is S1, this is S2. So entropy is constant, so it will be reversible adiabatic. Okay. So if entropy is constant, means it's a reversible cycle. So these are reversible adiabatic. Okay. 2 and 3. So this cycle 1, 2, 3, 4. 1, 2, 3, 4, 1 is a representation of Carnot cycle. So now come to the point. Area 1265 option A represents the heat added to the cycle. So we know that in a graph, we can like the area under the curve represents the complete interaction for that. Okay. So for suppose if we are talking about only 1 to 2, so the area under 1 to 2 will represents the total heat addition, because we know the 1 to 2 is heat addition. Okay. So 1 to 2 represent the isothermal heat addition. So the area under 1 to 2 will complete this area. Area 4365. Area 4365, this area. So this area will represent the heat rejection. Okay. Isothermal heat addition, isothermal heat rejection. Now area 1, 2, 3, 4. So suppose this total area okay. So this is representing suppose 1, 2, 3, 4. Okay. So area A is representing the total area for heat addition. Area B representing the total area for heat rejection. So remaining area 1, 2, 3, 4, A minus B. So this area will be remaining area. So this will represent the thermal energy that will be converted into work output. Okay. So option C is also correct. So basically all options are correct. So the correct answer is option B. And anyone can tell me what will be the efficiency of the Carnot cycle? Suppose the temperature, higher temperature is T1 and the lower temperature is T2. So what will be the maximum efficiency and Carnot?
1
Beta Carnot.
minus T2 by T1.
So 1 minus T2 by T1.
T1.
Okay. So this will be the efficiency of the Carnot cycle. So question number 5. So we have a numerical. A heat engine is deployed between two heat reservoirs. The high temperature reservoir is at 652 degrees centigrade and the low temperature reservoir is at 30 degrees centigrade. The heat engine draws 500 kilojoule from the high temperature reservoir and rejects heat to low temperature. What is the maximum work that can be produced? So always, whenever you try to solve the numericals of thermodynamics, always remember that you have to convert the degree centigrade into Kelvin. Okay. So always work with the Kelvin. And the second thing is that always read question carefully because here we have mentioned that what is the maximum work that can be produced. So they have given you a hint like maximum work. Now you have to think that when can be the maximum work will be there. Okay. So in thermodynamics, the Carnot cycle is only cycle that can represent the maximum work. So try to follow the Carnot cycle principles and try to solve this question. You have 2 to 3 minutes. Yeah, take your time.
It's 336.2 kilojoules.
Okay, let's wait for 1 or 2 more minutes. The others are solving. Anyone else? We have one answer as option C. Anyone else want to add any answer to this question?
Sir, 336.2 kilojoules. Option
Oh,
C.
nice. We have to answer now. So the correct answer is option C. So let's see the solution. Okay. So to draw maximum power, the device should carry out all the process reversibly. Okay, so it's mentioned here. What is the maximum work that can be produced? So we have given a condition. So if we are talking about the maximum work, then we have to consider all the process as reversible process so that the cycle will be a Carnot cycle. Okay, so we know that the efficiency of Carnot is that W max, okay, upon Q. So from here we can find W max. So W max will be efficiency of Carnot cycle into Q, added heat. So the efficiency of Carnot cycle, as we have also seen in our previous question, that efficiency will be 1 minus T lower upon T higher. So 1 minus T1 upon T2. Okay, so T1 is the lower temperature, T2 is the higher temperature. You can say TL upon TH multiplied by Q. Here you can see in the question that there are two reservoirs, one at 652 degrees centigrade, one is at 30 degrees centigrade. So you can imagine like this. In last class also, I told you that whenever you solve a thermodynamic question, always draw a simple schematic in which you can mention all the data like this. Here you can mention the temperature 652 degrees centigrade, it's 30 degrees centigrade. There is some heat addition to it, 500 kilojoule. Okay, now you can easily recall that there will work produced, there will be Q2. Okay, so from this I think you can remember what is the efficiency formula and what is what. Okay, you can not maybe you will not confuse about Q1 and Q2 because it's clearly mentioned the heat engine draws 500 kilojoule from high temperature reservoir. So high temperature reservoir is this one. So this one is Q1. So this is heat engine. Your heat engine is delivering some power. So from this you can recall and convert the degree centigrade into Kelvin. So here you can see 1 minus 30 plus 273 upon 652 plus 273 multiplied by heat addition Q. So it will be 336.2 kilojoule. So this is the correct answer. So correct option is option C, 336.2 kilojoule. Anyone having any doubt? Okay, let's go to next question. So question number 6 is a heat source at 527 degrees centigrade loses 2000 kilojoule of heat to a sink. So there are two conditions at a temperature 227 degrees centigrade, option B and B case, temperature 477 degrees centigrade in separate processes. So there are two processes in which the heat source is losing heat. Which heat transfer process is more irreversible? So you have to find out which heat transfer is more irreversible. So try to sketch a basic schematic for both A case and B case, and then you will have a clear picture for the question and you will be able to solve it more accurately. So you have to find out about irreversibility, and I think in our previous questions we have discussed about irreversibility. So try to remember those questions and try to remember those inequalities. Maybe those can help you.
Heat transfer to the sink at 477 degrees centigrade will be more irreversible.
So you are saying the correct option will be option B.
Yes.
Okay.
Option D, sir.
Option D cannot be said. Okay. Maybe you can take 1 or 2 more minutes. Try to rethink, because we have contradictions here. Because one is saying option B and one is saying option D.
Option B, sir.
Okay, so we have two answers as option B. So the question is, heat source as 527 degree loses same amount of heat, okay, to a sink at 227 degree centigrade and 477 degree centigrade. So which heat transfer is more irreversible? So you are all saying option B. So try to think in a perspective that without solving, I think we can tell that which option it could be without moving any like without writing a word.
Sir, because the 477 sink temperature is greater than 225, so his chance
Okay.
he release the conversion of the work is less in 477. So you can
Okay.
go with that, no? Option B. Visibility is ज़्यादा more in 447.
Okay. So you can say irreversibility will be more.
Yes, sir.
Okay.
If the temperature difference is more, so his
Okay.
visibility is less. If temperature is the sink and source is less, then his visibility is the more.
What is the reasoning behind this?
The temperature difference between source and the sink.
So
If
suppose
more,
if temperature difference is more, suppose just you can take an example. Like if you are like uh, we can take an analogy of temperature with a distance. Okay. Suppose you have to. Are you joined from two devices? Please mute your other device, because maybe I am hearing my sound.
sorry, sir.
Okay. So suppose we can like we can do a simple analogy here. So you can think of like temperature as a distance. So suppose if you have to move from A to B, okay. So and it is like 10 meter, and this C to D is 5 meter. Okay. So every like condition is same. You have to move this block. There is some block of 5 kg. Again, this block is 5 kg. So you have to move this block from A to B for 10 meter and for 5 meter. So in which case you have to do more work, and in which case there will be more friction.
10 meters, sir.
10 meter, because you have to do more work because the distance is more, and the friction will also more because the surface is again 10 meter. So if we talk about losses, then the loss will be more in this case as compared to this case. Okay. So same analogy can be applied here also, because if the temperature difference is less, it means that you are doing maybe just you have to transfer the both are near actually. So irreversibility will be less as compared to the more temperature difference. And how to prove it numerically? Let's see. So the correct answer is option A. Heat transfer to sink at 227 degrees centigrade is more irreversible. Let's see the solution. So the entropy generation is measure of the reversibility of process, we know, because entropy generation is the only measure of irreversibility. So we have to find out the entropy generation for both process. Okay. So the entropy balance for heat transfer to the reservoir at 227 degree is, what will be the entropy generation? Entropy of the source plus entropy of the sink. We can draw a simple schematic. So your source is, suppose, at 527 degree centigrade and your sink is at 227 degree centigrade. So there is heat. Okay. So from you can see from the source, the amount of heat is leaving. Okay. And at sink, the amount of heat is added. So at source, the entropy will decrease. At sink, entropy will increase. So entropy, we know that it is Q by T. So for the source, Q source upon T source, for sink, Q sink upon T sink. So for source, because the amount of heat is 200 to 2000 kilojoule, it is leaving. So we take minus sign, minus 2000 upon T source 273 plus 527, because you have to take temperature in Kelvin, plus Q sink, because heat is added. So entropy will increase. So it's positive. So 2000 upon 273 plus 27 Kelvin. So it will be minus 2.5 plus 4. It's coming at 1.5 kilojoule per Kelvin. So the entropy generation is 1.5 kilojoule per Kelvin for the temperature difference between 527 to 227 degrees centigrade. Now come to the case 2. If the temperature difference is 477 and 527. So now suppose this sink is at 477 degree centigrade. Now see the calculation. So you can see the entropy generation is only 0.2 kilojoule per Kelvin. So clearly, so what this entropy generation is representing? So anyone want to describe that? What is the meaning of this 1.5 kilojoule per Kelvin? What is the meaning of this?
It signifies a irreversibility.
Yeah, I know that it's representing the irreversibility. Okay, but what this data say? Actually, if I read that 1.5 kilojoule per Kelvin, what is the meaning of this? Like, what is the
It's an
significance?
increase in
Yeah,
entropy, sir.
in technical terms, you are saying correct. It's irreversibility, or you can say entropy. But in simple term, like, I am not from the thermodynamics. Okay, I'm a simple person. I don't know much more about this irreversibility and entropy. Now you have to explain to me. So how do you explain, like, what this is representing, this data?
Set loss,
Sorry.
some kind of loss.
Again, I don't know the laws. Try to simplify it. You know the answer, but you have to simplify it. Just take 1 or 2 minutes. Just think about it. Because just go.
No,
Just
I'm
see
telling
the
it's
picture
like
again.
loss in the thermal energy I'm talking about.
Okay. Yeah, you are talking about laws. It's correct.
Loss.
Yeah, laws is correct. But try to, like, more precise. Like how more we can interpret it. Yeah. Okay. So
It is a
basically,
disorder, sir. Disorder.
yeah, disorder is also entropy correct. Disorder is correct, but I'm trying to asking, like, in very simple words, how will you explain it? Like, there are two options: 1.5 kilojoule per Kelvin and 0.2 kilojoule per Kelvin. So in very simple words, without any technical terms, try to explain it. Then you will understand the entropy. Because we know that entropy is having so many definitions. If I ask the entropy, what is the meaning of entropy, then maybe every one of you will tell a different definition. Maybe. But what is the significance? Like what is this value is showing actually? 1.5 kilojoule per Kelvin, and for the other process it is 0.2 kilojoule per Kelvin. Okay, actually it's very simple. You have to just see the unit. So what is the unit? It's kilojoule per Kelvin. So this data is representing that for 1 Kelvin difference, okay, for 1 Kelvin temperature difference, the energy lost is 1.5 kilojoule for the process in which the heat is losing from 527 degrees centigrade to 27 degrees centigrade, and 0.2 kilojoule per Kelvin energy is losing for the temperature difference between 527 to 477 degrees centigrade. So from unit only you can see. So this is showing the heat loss per Kelvin. Like suppose if you are changing, like if you are going from 227 to 228, okay, so there is a 1 degree of 1 Kelvin of temperature difference. So if you are transferring heat only for 1 Kelvin temperature difference, then you will lose 1.5 kilojoule, and in this case you will lose 0.2 kilojoule. So this is the meaning. So it is showing you the like unit per unit temperature what will be the loss of energy. Okay, so by this we can compare between the different temperatures. So in our last class also I told you, if we are transferring heat from, if we are suppose if our waste heat recovery is at high temperature, okay, if our waste heat recovery is at high temperature, suppose 600 degrees centigrade, then we can extract more heat, okay, as compared to 400 degree temperature, okay, because the quality of the energy at high temperature is more. Okay.
Sir, I have a doubt.
Sir.
Okay, it's like see, suppose if we are representing this one on a TS cycle,
Okay.
on a TS cycle, if we represent, so we are talking that see at 527 degrees centigrade, if you are drawing a line and if you are creating some kind of, see, one example will be there. No, so it's like you can see that the change in entropy for that 477 degrees centigrade will be large, and the change in entropy for the 227 degrees centigrade will be less. So some kind of example they will be giving in our lecture also, in our video lecture also. So from that, is that different from this some?
Maybe I think you have to again see that video. Maybe they're trying to maybe explain some different thing, maybe, and maybe you took some misinterpretation, maybe. But
Yeah, why am I telling? Because I think I have taken for the entropy change of the reversible thing, reversible cycle, and this is entirely
okay.
different. This is entirely entropy generation concept. I'm assuming.
Yeah.
So it's
Maybe
like I think
please.
that's the
Yeah,
thing
please.
it went wrong.
Yeah. Please visit again. Yeah, because it's like as I told you initially. Because in first class also I told you, high grade, like the quality will be more at high temperature. So without doing this all calculation, okay, with only the temperatures you can see, like if you are covering a very less temperature difference, so you are covering 527 to 477, and now you have to go only maybe around maybe 60 degree 50 degree only down, and in the second case you are going up to 227 degrees centigrade. So basically you are going up to more, so there is a huge temperature difference is there. Okay, so there will be more entropy generation because there will be more irreversibilities. So the irreversibility is automatically more in the option A. And this is the like you have to find out the entropy generation. Okay, now I think it's clear
Sir,
to everyone. Yeah,
sir,
please.
can you can you explain the entropy? What is entropy in general word?
Entropy is,
Simple words.
as I simply told you, entropy is just saying that how much of energy is destroying. Okay, is, you can say unavailable. Okay, So like in our case, the entropy generation is 1.5 kilojoule per Kelvin for case A, for this case. So it means that if you are there is a temperature difference of 1 Kelvin, then there will be loss of energy of 1.5 kilojoule. Suppose there is body A and body B. Okay, it is at 550 degrees centigrade and it is at 449 degrees centigrade. Okay, so from going point A to point B. Okay, if you know if you know all the heat transfer coefficient and everything, okay, you know the temperature difference. Okay, so you can calculate the heat transfer. Actually, you can calculate this Q. So suppose this Q should be 1 kilojoule ideally. If the cycle is reversible and there is no entropy generation, there is adiabatic, there is no surrounding heat transfer, okay, everything. But in actual case, this Q will be 2.5 kilojoule. Why this 2.5 kilojoule? Because when you transfer heat from A to B, there is surrounding also. So there will be some interaction with the surrounding and some part of the heat transfer will get lost in the surrounding. So that lost heat will be 1.5 kilojoule. So 1.5 kilojoule will be lost in the surroundings. Okay. So net heat transfer only 1 kilojoule. Looking for this temperature change. But you have to transfer 2.5 kilojoule because 1.5 kilojoule will be lost in the surrounding and the 1 kilojoule is for this temperature difference. So net is 2.5 kilojoule. So basically entropy is presenting the irreversibility and it is showing the amount of heat that is not available to work or that is lost. That is entropy. Okay.
Can you tell the entropy losses of heat?
Sorry.
So can you explain like that ki entropy generation is the losses of heat?
Yeah, because entropy will only occur with the heat transfer normally, because the work there will be no entropy generation with the work because work is high grade energy. Okay, if you are transferring work, then there is no entropy generation. Entropy generation occur with the heat transfer. Okay, because heat transfer is low grade energy. So when there is an interaction with the surrounding and there is heat transfer involved, then there will be entropy.
Sir, then you are saying that for this finite temperature difference of 550 to 499, if you
Yeah.
want to transfer 1 kilojoule of energy, this 1.5 kilojoule of energy is like mandatory thing which you have to pay to that surroundings.
Yeah.
Is
Yes,
that thing?
correct.
It's like
With given surrounding condition.
System with further surrounding condition. It's like
Then it
if
will
you're
change.
talking about
Then
this.
it will change. It depend on surrounding actually. It depend on surrounding. In this case, this 1.5 kilojoule, we are taking only the heat Q. Okay, and only the temperature of A and temperature of B. We are not considering the T0 temperature. Okay, point to be noted. We are not considering T0 temperature. We are only considering the amount of heat transfer. And we are just considering the temperature A and B. Okay. Then this 1.5 kilojoule is there. If we also consider this environment temperature also T0, then it will be more actually. Little bit more. If we are considering the surroundings also. In this, the surrounding is not considered. You can see we are considering only source, T source, sink, T sink. Then this is the case. Because if you are drawing heat from the sink and transferring, then they are just considering the heat interaction between two only. If you are considering T note also, you have to go deeper in the class notes and you can refer some reference book in which there will be more explanation about this. But just in simple terms, entropy is just the heat loss due to the heat interactions. Yeah. And that is the unavailable energy that is not used for the work. That is lost due to doing some heat transfer.
Sir, can I
think
ask one thing?
Yeah, please.
Sir, same question. If in the process to replace by the engine, then what
Okay.
will the answer? Option A, B, what?
No, actually, engine is also a kind of in engine also there's a different kind of process occurring, na?
Sir, okay, but entropy generation
Yeah,
is
yeah.
a like that, na? That 527 is the source, and then 227 is the sink, and 476. So if the Q1 is 2000 Q1 is comes in the engine, and out of the
Okay.
Q2 is out the different temperature 227, 447. So 227 temperature is the produce more work, engine is produce more work. Engine will produce the more work compared to 447. So irreversibility is less, no?
Okay, I think you are saying like this. Let me just understand your question. Let me just redraw it. What I think I'm getting your point. Let's discuss it. Okay.
Sir, it's like the interpretation which I said, right? I was also confused with that interpretation, and I said it's option B.
Okay,
There is an
I
engine
think
which is transferring. I can help
okay.
you with that. If
Yeah,
the
I think
source temperature is 527,
you are saying like this. Okay, you are saying like this, na? This is some engine. It's
Yes, sir.
producing work.
Yes, sir.
Yes.
Okay.
Yes, that kind, yeah.
Okay, so it's okay. So I think you got to notice one thing actually here. Yeah. If this engine will produce work, okay, then there will be Q2 also. So are you having any Q2? Because for engine to produce work, there will be two things. If you are taking Q1, then there is W work output and there is Q2. So you are considering 527, okay. You are considering 227, it's also okay. Then you are considering 2000 kilojoule. So basically you are considering Q1, okay. So you are considering 2000 kilojoule. Now I think you are applying the Carnot efficiency here. Am I right?
Yeah, we are fixedly saying that we are getting the maximum work, so we are equating where you will be getting the Q2. So it's like we are saying that the cycle is reversible cycle. Obviously, the entropy generation will be zero then. It's like if you are
because
taking
entropy
that kind
generation
of
will be
significance means.
zero. Yeah. But it's not mentioned that the process is reversible. Okay. We are talking here about first thing is heat transfer. Okay. Which heat transfer? Because in this it is not given in the question that we are producing work. We are not producing any work because for producing work you have to place a you have to place a engine. Okay. Then there will be Q2 also. There will be W. Okay. And here we are talking about heat transfer. So there is direct interaction. There is no engine. There is only Q1 involved. Your 527, there is some system that is doing the heat transfer and directly there is 227. So there is only just heat transfer, this Q. And if you go through this like Carnot cycle, if you calculate 1 minus, if I calculate the TL upon TH, so what will be the efficiency for this case? Anyone? Anyone please calculate 527 and 227. What will be the efficiency for case 1?
37.5.
37.5.
37.5.
Okay, for case 2, the temperature 527 and 477.
10%, sir.
Okay, 10%. Okay. So what this efficiency is representing? Now now you will also now you will answer your question actually. Yeah. Now what this efficiency is representing? What is the 37.5% is meaning? And what is this
What
10%
is given?
is the meaning?
What is given that is the 37% convert is the work.
Yeah. So
It's given the
suppose
100 kilowatt.
yeah. Suppose this 2000 kilojoule you are having energy. Okay. So this process 527 to 227 will convert this 2000 multiplied by 0.375. Okay, equals to some value will into work, and remaining heat will go into the as Q2. Okay, and this is representing only 10%. Okay, but see the thing here. Okay, because because as I told you, okay, the simple analogy.
It's like both are reversible cycles only. One is
750.
giving
Yeah,
more
yeah,
work, one is
both are
producing
reversible
less work.
cycle. If
Both
you
are
are
reversible
moving
though,
more,
we
then
are
there will be more
fixing
work.
nothings.
Yeah, it's simple actually. If you are,
The
I told you na, there is a
friction
10-meter
concept will not
path.
come here. It's zero there.
Yeah, it's 5-meter path here. So if you are moving in a longer path, then you have to produce longer. You have to apply more force. In this case, you are going from a lower temperature difference. Then obvious, you will have more efficiency. But its efficiency is only representing. It's not representing about the cycle. Point to be noted. This efficiency is representing that how efficient is your system. Okay, it's reversible and it's converting your energy like 37.5%. Okay, so this 10% is saying that if your sink temperature, okay, is at 477 degrees centigrade, it means that your sink is still have energy because 477 is a high, you can say a high degree centigrade. Okay, so but you are considering it a sink. Sink means waste. That's why efficiency is low. Okay, point. Please note the point here because you are considering this 477 as a sink. That's why this subject is there. Waste heat recovery. Now I think you can consider what is the waste heat recovery. Suppose if you are having 10% efficiency only, but actually you are having temperature at 477 degrees centigrade, and this temperature is a high temperature, so you can utilize heat because you can see from the Carnot cycle that if you go up to 227 degrees centigrade, you can produce more heat. You can get 37.5% of efficiency. So still there is 27.5% of energy recovery chance. That is the waste heat recovery, and that is this subject is about. I think now you all understand what we are covering here. So we are covering this. We are covering the waste heat recovery. You are considering a very high temperature as a sink, which is not favorable for your plant, which is not favorable for our system. So we have to try to lower the temperature. Okay, so we can transfer the heat, so we can get more energy recovery. I think it's clear to everyone now.
Yes, sir.
Yeah, I think it's clear to everyone. Yeah. So basically, if you take this temperature as suppose just 100 degrees centigrade, then efficiency will be again more. So still at this temperature, you can extract some amount of heat. But it's not talking about irreversibilities. We are considering all cycles are reversible. This data, this 37.5, this 10% is only showing how efficiently you are getting the heat. How efficiently you are converting the heat into work actually. That is it showing. Okay. So there is also a note. So the entropy change for heat transfer for the reservoirs at 477 degree is smaller. Therefore, it is less reversible. Okay. Question number 7. During a reversible process from 1 to 2, the change of entropy. Go through options A, B, C, and D. Take 2 minutes.
Option B, sir.
Okay, just wait 1 or 2 more minutes.
Sir,
Yeah.
sir, can you share this problem with us?
Yeah. We will share it. I think you will receive a proper sheet, a Google sheet maybe, or yeah. Please, I request you whenever you speak, please mute the other device because I am able to hear my sound itself. Yeah. So I think NPTEL team will share a video link because this like this live session is being recorded. Okay, so I will upload this live session recording on YouTube and there will be a link. Okay, and I will also upload this PPT on Google Slides and they will share both the link of video and the slide and you can access that. I think I for previous week also I have shared. So if you have not received a link from NPTEL, then I think you should mail. And first, please check your mailbox because there will be a link for sure. There is a common sheet in which there will be every week's video link and a common folder on Google Drive on which you can access the PPT of the every live session after the session. Because today I
Excuse
think
me,
we are
just
having the
a-
session, so by the Monday or by the Tuesday, you will get the link. By Monday, I think.
Excuse me, just I want to confirm with the other participants. Did anyone receive such kind of link? Because if I might be wrong, I didn't receive the link. So I want to confirm with the other participants. Did anyone get the questions or the video recording session which we have, which had taken place last week?
Okay, if this is the case, then I will talk to my NPTEL team and I will let you know. Yeah. So maybe they will share by Monday. I will mail them today that the participants have not received the link. Okay, so maybe there is some misconfusion or error. So they will rectify it. Yeah.
And one more thing, can we get the PPT, this PPT presentation, can we get as a file instead of a video?
No, you will get a file. Yeah. You will receive a video in which like the discussion we are having, you can see the discussion. Okay, and you will also receive a PPT. This complete PPT which I am showing here, you will receive this PPT. So you can also try these problems at your home also. Yeah.
And one more thing, how can we approach you, Mr. Amit? It's like if you have any doubt in the questions, I think if we want to approach you, is there any medium for it?
Yeah, I think on video you can post some comments also, and there is a I think for this course there is a forum. I think the course forum is there, so you can upload your doubts on the course forum. I think, yeah.
Okay.
So maybe I will address that, or maybe some other TA. You can mention my name also. Maybe I will receive the link, so then I can address the question. Yeah, no issue.
Sure. So coming to the answer, it's option B from my side also.
Okay. I think we have given you the enough time, everyone. And anyone else want to add the answer? Okay. So the correct option is option B. During a reversible process from 1 to 2, the change of entropy will be equal to 1 to 2 reversible del Q by T, as we know. Because if it is less than, then it will be What it will be? What options is representing? Anyone?
It's like greater than cyclic integral of 1 to 2. The integral of 1 to 2 dq by t means it's irreversible thing. Greater than means.
Yeah. So that, because please see the one thing, that every time here is mentioned reversible. Okay, reversible. Okay. So this is for irreversible. This is not possible if the reversible sign is not here. Okay, but for reversible, this is correct. Okay, it will be equal to 0 for cyclic integral if we are talking for a complete cycle, but here we are talking about only for a process 1 to 2. So the cycle integral is not here. For process, it's 1 to 2 del q by t reversible. So the correct option is option B. Again, a numerical. Okay, so an adiabatic vessel contains 2.5 kg of water at 20 degrees centigrade. By pedal wheel work transfer, the temperature of water is increased to 30 degrees centigrade. If the specific heat of water is assumed to be constant at 4.187 kilojoule per kg, the entropy change of the universe is. Yeah, good question. Yeah. So point to be noted here, you have to find out the entropy change of the universe, and universe means system plus surrounding. Okay. There are like two type of entropy: entropy of a system and entropy of a surrounding. If we are talking about entropy of a system, then we are not considering the surrounding. Like in our previous case, in our previous numerical, we were only discussing about the source and the sink. Okay, we were not bothered about the environment. So basically, we were only dealing with the entropy of the system. Okay, because we are only discussing the source and the sink and the heat transfer between source and the sink. So we are not bothered about the surroundings, but here we are talking about entropy change of the universe. So we have to take the system entropy and a surrounding entropy. Yeah, please take your time.
It's option B.
Option B.
0.
Option B, very quick. Yeah, please. Just wait for 1 or 2 more minutes.
Option B, sir.
Okay, we will see. Okay, let's see the answer. So the correct answer option B. So this is the solution. So we have to find out the entropy change of the universe can be written as entropy change of system plus entropy change of the surrounding. So system's entropy will be, we have know that MC log T2 upon T1 plus 0. So why the surrounding entropy is 0? Anyone want to tell me?
Adiabatic
The system
vessel.
is the adiabatic vessel. So
Okay.
Q is transferred to the system to surrounding is 0. So that means del S is 0. Q by T is equal to 0.
Sir,
Okay.
the
Yeah,
adiabatic
anyone
vessel
else?
is considered here.
Okay. But there is a work transfer, na?
Okay.
Suppose there is a temperature increase, adiabatic vessel is there, okay, but there is a work transfer. So why the entropy change is 0 for surrounding? It's adiabatic, I get your point, but still you can see the temperature of the vessel was 20 degree, but it is increasing to 30 degree. So some amount of heat is coming to it, na? So from where this heat is coming? How if you are saying there is no heat transfer, then how the temperature is increasing? It's adiabatic. You are saying there is no heat transfer. So how
So
the
it's
temperature
like I
is
can
going
say
from 20 to
that
30
The
degrees?
work of the pedal,
maybe the paddle
pedal
work
wheel.
converted to
Okay.
heat. Conversion
So
of the
the
paddle work to the heat increase, which is increasing the temperature from 20 to 30 of that system.
okay. So this pedal wheel is inside the system or it is on surrounding?
The pedal is the inside the system.
Okay, so pedal is inside the system.
Yes, sir.
So how are you powering the pedal?
Electrical
So
work.
basically my question is that we are giving some work from a pedal wheel, okay, and maybe that pedal is receiving work from outside the system. The point is that because inside the adiabatic vessel, if you are completely considering that is the system only, let me draw a simple diagram. Suppose this is your system, okay, this is your vessel, and you are saying everything is inside. So then there is no work transfer also. So how are you increasing the temperature? Because if nothing is coming in, then how
So I
the
think
temperature will
for the
increase?
work transfer, we have to check at the boundary, right?
Okay. So this is the vessel, okay. It is having some gas composition. There is some pedal inside, and it is having some work. Okay. So it is rotating actually. It's rotating. So it's giving
Then
some energy to the inside. Okay. This pedal wheel is rotating. So the friction is increasing and the temperature is increasing. That is happening here. Now tell me one thing. You are considering this is as a system boundary. Okay. But still, this pedal is receiving work from outside, na? That is surrounding. So why we are taking it 0? My question is that. And some of you are saying that I think the pedal is inside the system, so that is wrong actually. Because if pedal is inside the system, then there will be no temperature increase. Because if you are considering a system that everything is inside it, then you cannot increase the temperature. Because nothing coming in, nothing coming out, nothing is going out, then they will be in thermal equilibrium. I have already told you the answer. Just think about it.
there is an internal change in energy, sir. Internal energy changes.
Yeah, there is internal change in energy. I know that. But how that internal change in energy is happening? That is happening because of the pedal wheel work transfer. Okay. But why? Because this pedal wheel is getting the energy from outside, na? My point is that.
So you're telling that there is an interaction between the system and the surrounding in the form of paddle wheel work.
Yeah, pedal
right?
wheel, correct. Yeah,
So
right.
you're telling that why there is no entropy change of the surrounding, though there is an interaction between system and surrounding. You're telling, am I right?
Yeah,
Is that the
correct.
question?
Yeah, correct. Okay, just take 1 minute
Sir,
only.
can I? Okay, I don't know whether it's correct. I don't know whether it's right or wrong, but if I talk, whenever we talk about entropy, it's like we'll be mainly referring to the kilojoule per Kelvin. It's like the energy in the form of in that way. So it's like we are mainly focused on thermal energy interaction.
Yeah. But you have to answer it correctly actually. Yeah. But you are not say like this. You have to say like work is a high grade energy. Okay, and there is
High
no
grade.
entropy generation with the work transfer. I have already
Okay,
told
okay.
you in our previous questions. So here, although the
You're
pedal wheel
telling
is
that entire
interacting with the
heat can be
universe.
converted into work.
No, entire work
Heat
can be
cannot directly
converted into
convert
heat.
into converted into
Entire
heat. Yeah,
work,
yeah, I
yeah,
got it. Yeah.
yeah, entire work can be converted into heat, but not entire heat can be converted into work. So
Converted
that
into
the
work.
work is high
Okay.
grade energy and the heat is low grade energy, and there is no entropy generation with the high grade energy. That is the point. So although the pedal wheel is interacting with the universe, but there is no heat interaction, there is only work interaction. Okay, and there is a mechanical work. You can see the wheel is rotating. So there is a mechanical work transfer. You can see this is a complete road. Okay, half of inside the system, suppose this is the system, and half road is outside the system. So do you think that this particle will rotate at different RPM as compared to this particle? What do you think? If this pedal is rotating, so this particle A, that is outside the system boundary, and this particle B, this is inside system boundary. This pedal wheel is rotating with 10 RPM. So tell me one thing, what will be the RPM of point A and what will be the RPM of point B? Is it same or there will be difference?
Same.
Yeah, because in mechanical work, the work is transferring completely. So from A to B, the RPM will be same because the pedal is rotating with same RPM. There's a mechanical work. There will be no loss in this work. Okay, because this pedal is completely rotating. This is the work transfer. You can just imagine it. Okay, because it's not interact. There is nothing difference. Both RPM are same. So the same work was available outside the system. The same work is also available inside the system. So this complete work is available here. So there is in surrounding, there is nothing lost actually. Okay, but it is not the case with the heat transfer. If you are transferring some heat from point A to point B, so suppose at point A their heat was available around 20 kilojoule, but if you this heat you will like cover this distance up to point A, then at point A maybe you will receive only 15 kilojoule. So that 5 kilojoule heat will transfer to the surrounding. But that is not the case with the work transfer because the point A will also rotate at 10 RPM as compared to point B. So the same amount of work that was available outside the system, same amount of work is available inside the system. So that the work transfer, the work interaction is having no effect on entropy generation. That's why the surrounding entropy is zero. I think it's clear to you.
So it's like entropy generation or surrounding entropy change.
Yeah, surrounding entropy change is also converting into entropy generation also. Na? Entropy, surrounding entropy, it's covering everything. It's also covering entropy generation.
Okay.
Yeah,
Okay.
it's
So
about
you're
total
finally
entropy.
making a point that if you're having converting from high grade to low grade energy, there is no need to pay anything to the surrounding. But if you are
correct.
doing from low grade to high grade energy, which is from thermal to work, you have to pay something to the surrounding. In the form of entropy change or entropy generation, some kind of loss.
Yeah, some kind of heat loss because some kind of heat will be lost in the surrounding.
Heat loss.
Yeah. Okay. Question number 9. So consider the entropy balance equation for a process as given below. Choose the correct options. So we have delta S equals to del Q by T plus S generation. So there are some statement. So go through all the options and let me know the answer.
I think D, sir.
Option D. Okay, just wait for one more minute.
Sir, option C, sir.
Option C. Okay. Let's see. Okay, let's start the discussion. So first, let's come with option C. So you are saying that option 1, 2, 3 is correct, but option 4 is like statement 4 is incorrect. So why? What is the reasoning behind it? Why the statement 4 is incorrect? So it's about reversible adiabatic process. So
it's like
do you want to tell?
option 1 and 2 are confirm it's correct, sir. It's like S generation, entropy generation is zero for a reversible process. It is sure. And
Okay.
S generation is a measure of irreversibility of the process. It's like the more and more entropy generation is there, the more and more irreversible is the process. So the first 1 and 2 options are sure.
Okay.
So coming to the fourth option, I have doubt in the third and fourth options. It's like.
Okay. So okay, you have cleared your, like, you are with option 1 and 2 only. So you are saying option B is correct. Now I think the other guy was saying option C is correct. Please respond why the option number statement number 4 is incorrect. Do you want to share your thoughts?
So 4 is also correct, sir.
Okay, yeah, I know you are saying it correct, but I think someone of you were saying that it's incorrect. Option C is correct. I'm asking to that person. Okay, maybe he's not sharing. Okay, so I think with statement 1, everyone is agree. Delta generation is 0 for reversible process, because if process, like there is a process, there is point 1, sorry, 1, and like we are coming to point 2 through a process. Okay, so from 1 to 2 it is reversible, so we can also go from 2 to 1, and the both state 1 and 2 are same. Okay, so it will be a reversible process, so there will be no entropy generation, because if you
Sir,
go
it's
from 2 to 1,
option D, sir.
so yeah, correct, option D. So the correct answer is option D. Now let's go for reasonings. So option 1 is correct, because if it's reversible, then there will be no heat loss to the surrounding, and there is no energy loss in, like, from going from state 1 to state 2, because if you go to state 2 to state 1, the all changes will sum up to the initial states. So the option 1 is correct. For for reversible process, S entropy generation is 0. Now come to the option 2. Entropy generation is a measure of the irreversibility. Yeah, correct. Because if there is entropy generation, it means there is a reversibility, and if the irreversibility is more, it means that there will be more entropy generation. If the reversibility is less, it means the system is very efficient and the entropy generation will be less. So if you are in a company, or if you are in a power plant or anything, so our aim is to decrease the entropy generation. If we decrease the entropy, it means we decrease the reversibility. It means that the available work is more. So the efficiency will be more. Your productivity will be more. So everything is connected. So our aim is to decrease the entropy. The third is del Q by T is 0 for a adiabatic process. If the process is adiabatic, and then it means that there will be no heat interaction. So delta Q will be 0. So that's why del Q by T will be 0. Now, if the reversible adiabatic, it's saying the adiabatic, it means del Q by T is 0. It is saying reversible, it means there will be no generation. So that both del Q by T is 0, S generation is also 0. So option 4th is also correct. So the correct statement will be D. 1, 2, 3, 4. Okay, I think it's clear to everyone. Any doubt? Okay. Again, numerical. A frictionless piston cylinder device contains a saturated liquid vapor mixture of water at 100 degrees centigrade. During a constant pressure process, 600 kilojoule of heat is transferred to the surroundings air at 25 degree. As a result, part of the water vapor contained in the cylinder condenses. The total entropy generation during this heat transfer process is, yeah. Just draw a basic schematic. Always remember, in thermodynamics, if you read the question, you will get confused. Try to make a simple schematic, then you can easily solve the question. Make it as a habit to draw a schematic.
0.4 kilojoule per Kelvin. Option
Okay.
B.
Option B, let's wait some more time.
Point 4, sir.
Okay, so now we have two answers. So I think we should move. So the correct option is option B, correct? 0.4. Now let's see the solution. So first of all, we have to write a entropy balance. So what is entropy balance? So entropy generation is equals to net entropy transfer by heat plus change in the entropy of the system. So you can draw a schematic like this. So this is the container, okay? So T is 100 degrees centigrade, H2O, this system, this surrounding is 25 degrees centigrade, and there is a heat transfer of 600 kilojoule. So generation will be Q rejected upon T system plus Q rejected upon T V. Okay, T system is the your temperature is it's 25 degrees centigrade. Okay, it should be, you can say, the surrounding actually. It is, you can say, surrounding, and this is for systems. Okay, so this 600 kilojoule is going from 100 degrees centigrade to surrounding. So the surrounding temperature, surrounding entropy will increase, and the entropy of the this system is will decrease. Okay, so you can say 600 upon 25 plus 273. So surrounding, we are taking a 600 as positive because there will be increase of entropy, because entropy will come with the heat transfer. Okay, so it will be 600 upon 25 plus 273. For this, the heat is going outside, so it's also taking the entropy with it, so it's decreasing. Minus 600 upon 2 plus 273. So it's increasing, it's decreasing. So it's come to 0.4 kilojoule per kg. So this is the net entropy generation. Okay.
Excuse me, sir, I have a doubt here.
Yeah.
Sir, if they ask what is the same question, if it is asked us, what is the change in entropy of the universe? So is that equivalent to the total entropy generation?
Yeah.
This actually I'm confused with these two words. Okay, suppose, see, if I say, they directly say that it's like change in entropy of the universe. Simply I'll say delta S of the system plus surrounding, where I'll be using the same things and I'll be getting the answer. So for the entropy generation also, is that the same thing? Change in entropy of the universe and entropy generation?
Actually, you have to read the question carefully. In this question, they are saying that during the constant pressure, the 600 kilojoule of heat is transferred to the surrounding. They are mentioning it. They are mentioning it actually, that the heat is going to the surrounding. And now you have to calculate total entropy generation. So they have mentioned that this heat is going to surrounding. They are giving you the temperature of the surrounding, and they're asking the total entropy generation. That's why you have to consider the system entropy generation of the complete universe. So you have to take the system plus surrounding, because they have mentioned it already. If they are not mentioning about the surrounding and they're only asking about the system, then you can say for system the entropy will be like this, minus 1.61 kilojoule. But total entropy generation, if you are also considering surrounding, then you have to find out like this.
Okay, I understood that. I'm asking that whether that is equivalent to the, see, delta, it's like change in entropy of the universe. If they have mentioned, can I use the same formula? I'm asking.
Yeah. If they have mentioned, you can use the same. Yeah.
Okay. Then.
Yeah. Okay. So entropy transfer is due to. Yeah. A good question.
Option D.
Yeah.
Option D.
B. Okay. So correct, because we know that there is no entropy transfer with the work, but yeah, mass and heat can transfer the entropy. So correct option is option D. Okay. I think I have put something wrong here. Okay. So which of the following statement is correct or are correct given the first law efficiency and the second law efficiency and the Carnot efficiency?
Option C, sir.
Option C. Okay, yeah, it's correct. Okay, so you can refer class notes and reference books. It's there actually. Okay. Question number 13. Which of the following is true? Option A is for work producing device. Second law efficiency will be useful work upon reversible work. For work absorbing device, second law efficiency will be reversible work upon useful work. Both of the above, none of the above.
Okay.
Both of the above.
Sir, C.
Okay. So, what is the meaning of statement A actually?
It's like we are comparing the actual work with the ideal work. If you are using any heat engine, it's like what is the ideal case, how we are getting, and what is the actual case. If you take the ratio, it's like second law of efficiency.
So the actual work will be less or more?
Actual work will be less, but the reversible work will be more. That's why we get in the form of efficiency.
Okay, and for the work absorbing device, the actual work will be less
Reversible
or
work will
more?
be less. Actual work will be more because we have to give more work than the theoretical one or ideal one.
Yeah, correct. Because there are irreversibilities. Okay. So when we are giving the work, then to overcome the reversibilities, we have to give more work. And when we are producing work, due to irreversibilities, less work will be produced. So the correct option is C. Both statements are correct. So an electric cluster heater for residential heating building is claimed to have an efficiency of 100%. Assuming an indoor temperature of 218 degrees centigrade and outdoor temperature of 10 degrees centigrade, the second law efficiency of the heater is. Please take your time. Any answer? Okay, so the correct answer is A, 3.75. Let's see the solution. So in this case, the second law efficiency of the resistance heater is given by the COP of heat pump and COP of heat pump reversible. Okay. So the heat pump, like in actual and reversible. So for reversible case, it is claimed that heater converts the total electric work supplied into heat. Okay. So what is mentioned here? It is mentioned that converts the total electric work supplied to into heat. So COP of heat pump is equal to 1. Now COP of heat pump reversible is given by, so 1 upon 1 minus TL upon TH. So you calculate it and you know it, the formula, it comes 26.7. So the second law of efficiency will be COP of heat pump upon heat pump reversible. So 1 upon 26.7, it comes to 3.7%. So 3.7 is not an option. So then the nearest is 3.75. So correct option is A. Okay. Okay. So a waste heat stream in a process industry of 250 kilowatt capacity is available at 400 degrees centigrade. The ambient temperature is 27 degrees centigrade. The exergy of the waste heat is. So you can consider it like exergy. So exergy and energy. Exergy is the maximum useful work, okay, available. We have to find out the exergy of the waste heat. So we are having some waste heat. We have to find out that how much of work can be produced from this heat. The maximum work, that is exergy, can be produced from this available heat.
It's option A, 138.5 kilowatt.
Okay, let's wait for one more minute. Maybe 1 or 2 are still solving. Okay. So the correct option is option A. Okay. Now we know the exergy is the amount of
Option
heat
A.
available. Yeah, correct. Amount of heat available multiplied by the what?
Carnot efficiency. So
Yeah, 1 minus T naught upon T1. Because this can be the maximum useful work from that heat. So that the exergy of the waste heat is Q into 1 minus T naught upon T1. So entropy is like an intensive, extensive path function, none of the above.
is an extensive property.
What is the difference
Extensive
between
property.
intensive and extensive?
Intensive
Depend on
is
mass or
dependent of mass.
Yeah, correct. So you know. So the answer will be option B. So quickly, we have actually only 5 to 7 minutes left, so we can go quickly. For a closed system undergoing an irreversible process, the entropy of system, what?
increase.
Read the question carefully.
So it can increase, decrease, or remains constant.
Yeah, because it is not mentioned that what type of process it is. It can increase, decrease, or remain constant.
Constant.
Yeah. Entropy is, yeah, we have cleared it. Okay. So what is the correct expression for system undergoing a reversible cycle?
Option C, D. C, option C.
C, correct. So quality of waste heat. Depends on temperature only, chemical composition
Option
only.
D. Option D, sir.
Option D, correct. Depends on both temperature and chemical composition. Yeah, because temperature quality is also as a high temperature quality is high, low temperature quality is low. Chemical composition, like it's if the waste it is having hydrogen, so we can use in combustion. If it is having some other combustible gas like CO, also we can use in combustion. Okay, so it's depend on the chemical composition also. If it's only having CO2, then it's of no use. It's only a greenhouse gas. Yeah. Option D. For the maximum useful work obtainable as a system goes to dead state. Is PD work, is the entropy, is the availability, or none of the above?
The availability.
Yeah,
Option
correct.
C.
So yeah, availability is the maximum useful work. The quality of energy utilization is determined by
Second law. Second law, sir.
yeah.
Second
So
law, sir.
quality is determined by the second law efficiency. Or the second law efficiency of a refrigerator is equal to
Option B, sir.
yeah, because the actual work will be more than the
More than the
reversible one,
reversible.
because the refrigerator is a work consuming device. Option B. Availability of system during a process.
So is that option
I think
C?
option C, sir.
Yeah, because in a process there will be reversibility, then irreversibility will destroy the available energy. So availability will be destroyed by the irreversibility. Figure of merit of heat pump.
Greater than one.
Greater than 1.
Yeah, correct. So I think we have covered. Okay, one question is still left. The correct statement regarding irreversibility.
So A is wrong.
Okay.
It's option D.
Option C is right, and option D is also right.
So what will be the answer?
C and D, sir.
It's option D.
So one is saying option D and one is saying option C and D. As the guy who is saying option D, please note that it's not mentioned in the question that only one option is correct. Maybe more than one options can be correct. So please rethink. Maybe option C is also correct. Is it so?
Yeah, option C is also correct.
Yeah, correct. Yeah, because always remember in NPTEL assignments and questions, more than one options can be correct. Okay, because it is not given in the question statement that only one option is correct. So you have to go through all the options. You should know all the reasoning behind every option, why the option is wrong and why the option is correct. Then only you can choose the correct options. Okay. So the irreversibility decreases the work done in heat engine. Yeah, correct. Because if irreversibility is there, then the work producer then the work output will be lower. Irreversibility is equal to T naught as generation. Yeah, as generation is entropy generation, and T naught is the temperature of the surrounding. So if you multiply the entropy generation with the surrounding, then you will get the actual irreversibility. Okay, because the unit of entropy generation as generation is kilojoule per Kelvin. When you multiply with the temperature, so you will get the answer in kilojoule. So you will get exact irreversibility in kilojoule. So I think it's enough for today. So I think everyone has enjoyed the session.
Yes, sir. Sir, one thing can explain entropy. It's a general word, sir. General word can explain the entropy. It's a labor word like it.
Entropy, just take a simple thing like loss of energy. You can say that. Okay, loss of energy per change of uh, uh, per unit change of temperature.
Sir, one more talk with this regarding the same question. They were telling that entropy is loss of energy, right? And one more statement I hear regularly is it is disorganized they will be telling. So can I say that this loss of energy is going converting in the form of disorderedness, means which is giving energy for the molecules and they are getting disordered?
Because you can
Is that
consider
the
like
way we can think?
if their randomness is increasing, entropy is also connected to randomness, disorderness. Okay, suppose if you are having some particles, okay, and that particles are in ordered form, okay, if they are in ordered form and suddenly they are disordered, okay, disorderness is increasing, so that it means that every particle is going like in any direction. Okay, when every particle will go in any direction, then what will happen? You can think like a crowd. Okay, if you are moving in particular rows, okay, then what will happen? There will be no touching. Okay, there will be no mess up, and you can easily move. If you are running in a row, you are running in lines. Okay, but suppose there is a stampede. Okay, and everyone is going like in this direction, that direction, then what will happen? Everyone will strike to one another, and in that, what will happen? They will someone will fall, someone will get injury, and like that. So there will more energy loss. So if the randomness is increasing, it means that particle of the systems are moving in any direction. So in that they will strike with each other. They will like in that striking motion and then interaction, they will lose some part of their energy. Because what is the heat transfer? What is the heat actually? If we go on to the molecular level, so the every molecule is vibrating. And the vibration is generating some amount of energy. Okay. So you can consider in that point of view. For more reference, maybe you can see
So
some
you are
videos on
telling
YouTube
that,
also. So in YouTube also some videos you can see, and maybe they can explain with you some more animation and all. Yeah.
so
Sir,
we can
what
say in this way,
what
suppose
the
there
way?
is a body with one temperature.
Sorry, please, one at a time. Yeah, Varun, please.
Sir, okay, can I summarize in such a way that, okay, if I want to send an amount of energy from one temperature to other temperature, okay, from higher to lower, so we can say that if you send in a correct way, the losses will be less, means the entropy or irreversibility will be less. Is that
Yeah,
you're telling?
correct.
So
Yeah,
the
yeah,
way in
correct.
which you are sending.
Yeah,
So that's why
because
which can be replicated to a waste heat recovery.
yeah, which is the waste heat recovery? Yeah, correct. If the suppose we are employing a system, okay, which is generating more entropy, it means that that system is not efficient. If we suppose if we can reduce the entropy, so it means that we can put a system that can transfer the heat in a more ordered way, or it means that there will be less entropy generation. Okay, that's why today we are not doing the energy analysis, we are doing the exergy analysis. In exergy, basically, we see which systems are having least exergy, sorry, maximum exergy and least entropy generation. So we are looking for exergy efficiencies. Whenever we do optimization of the systems, we go for the exergy optimization. Okay, in that we will try to reduce the entropy generation from the waste heat recovery from the systems. Okay, And in that way, we are increasing the exergy and we are increasing the net efficiency. Because if we are talking about the energy efficiency, that is not the actual efficiency. Because in energy, nothing is destroyed, everything is conserved. Okay.
Sir, sir, one thing can I ask
Yeah,
like
please,
that
please.
is okay. The topic generation and the inverse is increasing continuously.
Yeah, yeah,
Okay, that means the sounding is mostly increasing. So
yeah.
what's the way to recover it? Any way to recover it?
If the surrounding, you can like in surrounding, you cannot increase, you cannot recover that entropy, but the system, you can like decrease the entropy that is going from system to surrounding. Okay, basically you have to decrease the heat transfer, that is, and you have to optimize, you have to like efficiently transfer the heat from your system to surrounding, then only you can decrease the entropy generation. The one thing is that suppose like the chimney or stake. Okay, in in like in power plants, they are directly flaring of the exhaust gases, and maybe the exhaust gas is having temperature of around maybe 200 degrees centigrade, and they're directly flaring into the atmosphere is at 25 degrees centigrade, suppose. So the 200 degrees centigrade is directly going to 25 degrees centigrade without any heat exchanger, without any means, so that there is a direct interaction of 200 degree to 25 degree centigrade, okay, surrounding to system, so that there will be more entropy generation, maximum heat will be lost. And in that, suppose if you channel that 200 degree centigrade gas stream through a heat exchanger, and you supply cold water in that heat exchanger, so that maybe some amount of heat, the cold water will get, and that maybe the water can be heated up to maybe 80 degree, maybe 90 degree, and your exhaust temperature is about maybe 110 degree centigrade. Now you are sending the 110 degree to the atmosphere. Okay, so from that 200 degree to 110 degree, mean 90 degree, you have some of the heat from that 90 degree you have used to heat the water. In that way, like we are extracting the heat, so in this way we are decreasing the entropy. So we can put some means, like, so we can tap off the maximum energy. That is only the thing.
Thank you, sir.
Yeah. Okay. Okay. So thank you everyone for joining the session. I think everything
Thank you
is,
very much.
yeah. Welcome, welcome. So I hope everyone will also join on next session. So because if you join, then only we can discuss it, and we will discuss it. Then maybe some new doubts will come, and maybe I also get to learn from you also, because you are also having some unique doubts and unique response actually. So I'm also getting learn actually. Yeah, it's good. It's a very good thing to interact. Yeah. So I request everyone.
Yes, sir. Thank you very much for your answers and everything.
Yeah. Yeah. Thank you everyone for joining. I hope you all will be there on next Friday, again 7 to 9. Okay. Okay. Thank you everyone. I'm ending the
Thank
meeting.
you very much, sir.
Thank you.